Okay, class, the last section of this chapter is going to be about testing a claim about standard deviation or standard deviation squared, which is called variance, which we might remember from chapter 6. If you aren't certain, feel free to go back and take a look. So we have some assumptions that we need to start with. So we always assume our samples are simple random samples, and the population has values that are normally distributed, right? This condition of normality is much stricter because we're going to be working with chi-squared tables as opposed to z-scores and t-scores. So we're looking at chi-squared scores. So remember that the above test statistic is called a chi-squared, right? Where n minus 1 is our sample size, kind of like degrees of freedom, n minus 1. S squared is our sample variance squared, and our standard deviation squared is going to be our variance. And we use this chi-squared statistic to check variation between scores. So it comes from a chi-squared distribution, which is a little bit different, right? It looks like it's skewed to the right, okay? But there's a different graph for each degree of freedom. That's important to keep in mind. It doesn't always look this skewed. So these are going to be in table A4. This is going to be the chi-square values, right? It's going to be in our book A4. I also am posting one of these to our online platform. So for a right-tailed test, you need to locate the area at the top of A4 that's equal to our significance level. So if my significance level is 0.01, that's the area I'm looking for. It's going to be a right-tailed test. My critical value would be 29.141. And for if my test statistic was greater than 29.141, I would reject the null, because remember, this is right-tailed. So I want my value to be above what I've found. If my test statistic was less than this, then I would reject the null. If I'm conducting a left-tailed test, I have to find 1 minus alpha, okay? Then I'm going to locate the area at the top of A4 that corresponds to 1 minus alpha. So if my degrees of freedom is 20 and my alpha is 0.01, when I'm making a left-tailed test, right, I'm looking at the area over here, I want to look for the 0.99, because 1 minus 0, 0.01, is 0.99. That's where this came from. So look at the top of the page, and you should see a critical value of 8.260. So for any test statistic less than 8.260, this would cause me to reject the null. I'd want my value to be less than that. Things get a little trickier, though, when we're looking at a two-tailed, right? We did left-tailed, right-tailed. Now let's look at two-tailed. So for a two-tailed test, you have to calculate 1 minus alpha divided by 2 and alpha minus 2. Why alpha divided by 2? Why is that? So if I have a critical value of 0.05, I need to divide that by 2, and then I would have 0.025 on each end. Remembering that this then holds the middle 95% of data. So in this case, my alpha over 2 would be 0.05, would be 0.025, and my 1 minus my alpha would be 0.975. Where did this number come from? It comes from 0.025 plus this area right here to get to this value, 0.95. So any test statistics that's greater than the larger of the two, right, so greater or smaller than the 2 would cause us to reject our null hypothesis. So let's look at this example. Test and statistics class have had scores with a standard deviation equal to 14.1. So that's our population standard deviation. A current class now has 27 test scores with a standard deviation of 9.3. We're going to use a 0.01 significance level to test the claim that this current class has less variation than previous classes. So does a lower standard deviation suggest that the current class is doing better? Well, not actually. Remember, variation measures how much of a variance there is in scores, right? So just because one class may have a larger variation in their score doesn't mean that they aren't doing as well as a class with a lower variation. So let's prove this. So my null hypothesis is that there's no difference between the current standard deviation and 14.1, and my alternate hypothesis is that my new group has less variation. So I have all the pieces of information I need to calculate a chi-squared statistic. So we're going to go ahead and substitute in our n, which is 26. So 27. So 27 minus 1 is 26. Over times my sample standard deviation squared divided by my standard deviation squared, and that gives me a score of 11.31. So my critical value is 12.198. I found that by looking at degrees of freedom 26 and my area from 0.91 in the top of the column. That's because we're doing a left-tailed test. All right, guys, I had to go check. So that's because we're doing a left-tailed test. And we reject H naught since 11.13 is less than my critical value of 12.193. So because it's to the left of it, we can reject our H naught. What does this mean? So like I said, it doesn't mean the current students are doing any better than the previous one. It just means there's less variability or variation in their exam scores. So let's take a look at this one more time. So based on data from the National Health Survey, men aged 25 to 34 have heights with a standard deviation of 2.9 inches. And we want to test the claim that men aged 45 to 54 have heights with a different standard deviation. So we randomly selected 25 men, and we found they had a sample standard deviation of 2.34 inches, whereas before there was a population standard deviation of 2.9 inches. And we're looking that they have a different. So this means we're going to have a two-tailed test. So let's take a look at our null and alternate hypothesis. So we want a 95% we want a point alpha of 0.05 because it wasn't given to us. Here's my sample size, population standard deviation, and our sample standard deviation. My null hypothesis is that there's no difference in the claimed value in variance, and my alternate hypothesis is that it's different. So that means it could be less than, it could be greater than, but this leads us to do a two-tailed test. So I'm going to have to look up two critical values. So we calculate our chi-squared, and we have to find the two critical values. Where do our critical values come from? Well, remember, I have to take my alpha divided by 2, so alpha is 0.05, and I divide that by 2. That means I have 0.025 area in this tail, and then I also have to take 1 minus alpha divided by 2, so that means I have 0.975. Because the area in here is 0.95, and the area in here is 0.025. So this whole area right here is 0.9725. So we have 24 degrees of freedom because our n was 25. We find chi-scores of 39.365 and 12.401. So what do we do with that information? Well, we need our critical value to be less than the smaller one or greater than the larger one. Well, what did we calculate our chi-squared to be? We calculated our chi-squared to be 15.26, right? since 15.26 is not less than 12.401 or greater than 39.365, it's like over here somewhere, right? We cannot reject our null hypothesis because it's not less than or greater than. If it's in this interval, you do not reject it.